Welcome back, everybody. So we are going to continue with this introductory lecture. I just want to repeat what was said during the break by Andrea, which is that if you have trouble connected to the Element chat, please write an email to Andrea, and we'll resolve it separately. I think that a couple of you might have an issue. It's a known issue, and we'll make sure to thank you, Andrea, for pasting your address. So contact Andrea and we'll figure it out. For the others, you probably don't see yet the course chat. It's because I will invite you later this afternoon with the database that I have of the attendance list. Okay. So I will also say some questions that were asked during the break. It's a session exam. I do not have any information on the date. This is decided by the examinations office in November, December. And this will be then announced to everybody. This is something that is outside my control, so it's just going to be announced officially by ETH. Is there something else in the break that we discussed, or I think that's pretty much it, right? All right. Okay, so let's then continue. Information systems. So we want to build systems that process information. So what is information? Well, it can be language. Right now, I'm transmitting information to you, hopefully. It can be spoken, written. We can have drawings, diagrams, symbols, and so on, like even the clay tablets back then. We can have models of the world. This is typically also what in science, physical models actually do. As opposed to data, information, data. Data, I would describe as a raw form of information. A raw form of information. It's the actual bits that you store on a computer, that you send over the internet. It's the actual letters that you would have on a clay tablet or numbers and so on. So this is really the rawest form that you can have of data. This is why I'm using here as an example this raw material, so wheat, and here flour as a transformed version of this, right? So data can be stored and it can be exchanged. These are the two main things that you can do with that. In the system like PostgreSQL, so the database systems that we will look into, we will see that these systems take care of storing that data for you, right? Exchanging data, it's something, probably we'll not talk a lot about this in this lecture, but maybe more in big data for engineers. It's when you ship it over the internet. In fact, it could be that you download a CSV file from the internet that you then import into your Postgres database. That's also a possibility of something that could be exchanged, right? So it's whenever you download or upload data sets over the internet. So this is data. So you see, you have this full pipeline where you have the actual raw data that you download and store. Then you extract some meaning together with some context, for example, schema, taxonomies, and so on. And then when you find a meaningful application, you turn that into knowledge. This is actually when it's actionable, that you can actually make decisions based on that. All right, so these are the first three, and wisdom would be the last one. For this, we have the Science in Perspective courses that everybody has to take during your studies. Okay, so an information system, here I think I can remove this thing here in the lecture hall. Normally, I should have a way to make this go away. Somehow it will not. Maybe if I wait for a few seconds, it will. Let's see. Anyway, I can say it. So an information system is basically a system that is tailored all around information in order to store and process information for you. We'll see that it has a lot to offer that you do not get with a simple imperative programming language that just reads from the disk, which was the situation in the 1960s. All right, so this is what we are going to do during this lecture. So now I'm going to slowly dive a little bit into the material, but just on an abstract level, right? Because I'm not going to scare you already now with 14 weeks worth of material. So just a few words about the notion of data structure. So it's really like raw data, the structure of the data. I'd like to talk to you first about the concept of data shape. Data shapes are super important. Super important. Because data has a shape, just like matter has a shape. Whenever you query a data set or you want to work with a data set that you have downloaded, or whenever you want to create data, you need to figure out the shape that the data has. Why? Because if you pick the wrong shape, it's going to be slow. Slow because of performance, because the queries will take a long time, or slow because you building the system will take a lot of time. Because you're basically, you could consider it's called an impedance mismatch. It's putting a square peg into a round hole, right? If you pick the wrong data shape, you're going to spend more time than you really need to. So what shapes do you have? Do we have? Not so many of them actually, just 5. Tables are the first one. This is the most popular one, known for thousands of years. Then we have trees. Trees is something we see in big data for engineers. In fact, this is your question earlier when you asked about non-relational databases. And in fact, yes, there are databases that actually process data as trees. You might have heard of XML, JSON, YAML. Who heard of this? Many of you, right? So this is XML, JSON, YAML, and so on. And there are databases that deal with that, right? But this is big data for engineers. Then we have graph databases that directly work on graphs. So think of a public transportation map, or where you connect data like this. It's very popular for knowledge, for a knowledge base. When you try to automatically to design taxonomies and ontologies, and it's one of the ways to do artificial intelligence that's not machine learning. So artificial intelligence is bigger than just machine learning, and this is another way of doing artificial intelligence, right? Then we have cubes. In fact, cubes will be part of this lecture, as I said, at the end of the semester. Instead of a table, it's a cube, and you have dimensions, you can slide. It's really like a Rubik's Cube, right? Except that managed to get one that is not an exact cube. It's more like a cuboid, I would say. But this is pretty much what we will manipulate at the end of this semester. And the fifth one, what is it? You already saw it, actually. It's also thousands of years old. Text, right? Tables and text, these are the 2 shapes that we had on the clay tablets earlier. Text looks trivial, it's absolutely not. In fact, there's a lecture called Information Retrieval that teaches how to process text. So this is also something you can treat as a database problem, store text, retrieve text. It's in fact what a search engine like Google or Bing or Yahoo is actually doing. Okay, so these 5 shapes, remember them: tables, trees, graphs, cubes, text. Learn that by heart. It's very important to figure out which one of the 5 you are dealing with every time. You can actually place these 5 shapes on some spectrum of structuredness, I would almost say. So you have fully unstructured data, like a text. Then you have graphs that are a bit more structured. Then you have semi-structured data. It's the name we would give to trees or collections of trees. So NoSQL databases. This is often how we call this. Then we have tables. This is what we will focus on. And data cubes are the ultimate structure that you can get for your data, right? So you see all these 5 shapes arranged in order of how structured they would be. Yes, maybe with the catch box. And I will also increase the volume. Yes, I'm going to do my best to avoid the feedback loop. Go ahead. Thank you. So I think we had a sound, I understood you. We had a sound problem. I'm not so sure if it's a battery issue or if it's switched on. But no, that's okay. I will repeat your question. I understood you. We just need to look into it. So you wanted to ask more about what structured data looks like. Well, I have plenty of slides on that. So in fact, I'm going to talk a lot more about structured data today. So this is something that I will definitely get in the details on. In fact, this is the focus of the semester's course. So we'll have basically structured data all over the place for 14 weeks. So I don't know if this is enough that I answer in that way as a pointer to the future, but basically I will show you all of that to you, right? Is it okay? Okay. So you can think of the structure as the arrangements like this in a tabular structure, as opposed to like free-form text, that is just that you need to parse and extract the grammar and so on, right? This is the intuition of it. But we'll see. We'll see. It has to do with data modeling also. Okay. Okay. So, in fact, these coming slides pretty much address this as well. So, unstructured data can be text like this. This is probably some Sherlock Holmes thing because now it's public domain. So I just copy pasted some Sherlock Holmes excerpts. You can also have pictures that could also be, you could argue, let's say you could argue, but it could also be considered unstructured data in the sense that it's just, you know, all over the internet, you have text, you have pictures, you have audio, you have video, and so on. The reason why I'm saying you could argue about that is that if you look at it as a rectangle of pixels, then in machine learning, you could actually interpret it as some structure, you know, and that's the way that Photoshop and this sort of software are working. But from a point of view of databases in the classical sense, we might call them unstructured, nevertheless, okay? So these are examples of unstructured data. It basically doesn't have an explicit structure. That would be the characterization of that. There is no explicit structure. Everything is implicit. If you want to understand text, you need the notion of understand what a word is, what the grammar is, and so on and so on. There can be ambiguities in the language as well, and so on and so on, right? So everything is implicit. But you can build out of this data, you can turn it into something more structured, right? So this is what natural language understanding does with text, for example, or this is what machine learning does with the pixels of an image, right? But basically, everything is implicit. In the case of semi-structured data that's in the middle, you have data that is structured like a tree. That would be actually some JSON or XML in memory would be represented as a tree. You have structure in the sense that you have some names in here that you give to your data, and there is a structure like this with pointers in memory. Text wouldn't have that. Text would just be a sequence of characters, and that's it, right? But here you see it's more elaborate than just text because you have that kind of structure. So this is semi-structured. And in fact, in some cases, it's semi-structured, let's say on the plus side, that you can actually turn it into what is called a data frame. Who already heard of pandas, data frames, and so on? Right, that's pretty much what it is. So a data frame, I don't know if you've heard it put that way, but a data frame is nothing else than a validated collection of trees. This is what a data frame is from the perspective of databases. So we will not cover this in that course, but nevertheless, we have it here. That's considered semi-structured. You see, it's not exactly a table because here we have, again, this tree structure right there. You see? So it's not exactly a table. That's why semi-structured. And finally, fully structured in the sense of a table, you really have rows and columns like this, where it's nicely organized. This is, I think I picked some financial data from the SIX website. It's the Swiss exchange in Zurich. So you see there's rows, every company has one row, and then you have attributes right there. I will go in details about what a table is and how we characterize this structure next week. That's the relational model, right? So I explain it in detail. But basically the idea is there is a regular and fixed structure defined in advance. You can see it in particular right here with the headers that are right there. This here, we will see it's called the schema. And this is what gives the structure, because even as companies get added or removed, this here will not change. And you have the values all over there. This is structure. Does it at least partially address also the question you asked? Right, so just to speak again for those on Zoom. So you meant to ask more about what a cube looks like, right? Yeah. We need to re-invite. Yeah, I'll make sure to make you a permanent host. It's the first time actually that it keeps deconnecting like that. Usually it's just once, but yeah, thank you. All right. So cubes, what does it look like? Well, this is what we'll study at the end of the semester. Think of sales data, which would be the primary example for data cubes, where you have the sales of, let's say, phones televisions, all kinds of products sold in Switzerland, in Germany, in Austria, in Italy, in France, in the UK, and so on, in the year 2022, 2021, 2020, 2019, and so on. That's 3 dimensions, right? You could think of it as a table, of course, because we will see that you can actually visualize it as a table. But it actually makes more sense to visualize it. I go back to the slide, where we have here 2022, 2021, 2020, and 2019, right, along this dimension. Then here we have phones, televisions, and I don't know, computers, right, along that dimension. And here we have, let's say, Switzerland, Germany, Austria, and so on. Every cell of the cube, that's why I put a Rubik's cube in there. So this would correspond to 2022 in Switzerland for phones, this cell right there, right? This is 2021 in Switzerland for phones. This is 2022 in Germany for phones. This is 2022 in Switzerland for televisions. That's a cube. You could view it that way, yeah. But again, we'd spend 1 week going over all of that in great details, but that's pretty much the idea, yeah. Okay. So structured data, which we'll focus most of the semester on, means relational databases, and you can think of that as a spreadsheet to begin with, right? When you work with Excel or OpenOffice and so on. Okay. So now, when you want to deal with data shapes, which is just a general intuition, you need a model of the data. A model of the data is something that allows you to understand the data and look at it from a certain angle. You could consider that, for example, the map of a building is a model of the building, right? You could consider also that the maps that you find now on the internet are a model of the surface of the Earth, right? You also have, that's actually called the scale models, right? Where you build a miniature version of something. This here is a model. Does anybody recognize what this is? That's Schrödinger's equation, quantum physics. So this is also a model of that you have that you use to build theories and then represent reality or try to explain reality. Then you have economic models with all, they usually have these fancy curves of unemployment rates, like for example, these sort of things. All right. Well, in databases, it looks a bit similar, but this is what a database model would look like. Actually, it's quite popular to draw them in that way in companies. When you design a database, you basically model what your attributes are. So these are tables right here. These are all tables. They don't look like tables because it's just a model. This would be the list of the attributes that you have in a table. This is another table. This is a list of attributes. This is another table. That's a list of attributes. Then you have these rows that connect the attributes to each other. What does it mean? We'll see. That's part of what we will look into in this course, right? But basically, we can also model structured data like tables in this way with that sort of diagrams when designing the schema of a table. So overall, if I summarize these 5 shapes, we have the relational model that we'll see next week, the data cube model that we'll see in the end in this course. We have non-relational models that you asked about with the tree-like data models and graphs. So there's RDF, there's labeled property graphs. This is rather in NoSQL, and then this is information retrieval with text. So relational model, data cube model, these are the 2 we'll look into. Okay, now, what is an information system? Well, it's used at plenty of places, everywhere, in universities, supermarkets, banks, social networks, and so on and so on. A lot of information is flowing all over the internet, right? That was 6 years ago, and you can, if you compare the 2, actually, I didn't get the 22 yet. I don't know if it's been done, but you can compare. The difference is very impressive. How in just a few years, what people are using changes very fast. In order to explain this flow, one way to look at it is to, it's called the 3 V's: velocity, variety, and the volume, right? So right now we are looking at I think, exabytes or zettabytes of volume at the scale of humankind. These are actually prefixes to mean, you probably all know kilo, mega, gigatera out of computers, right? The sizes of hard drives. You should also learn these. These are the prefixes that go further all the way to 24 zeros, right? So let me say this is your first assignment next to learning the 5 shapes. These are the prefixes of the international system. How to remember them? You know numbers in Greek, right? Tetra, penta, hexa. It's actually probably coming from there with maybe they removed the letter just to do something different. But if you know tetra, penta, and hexa, then tera, peta, hexa should be easy to remember, right? How it happened is basically that there were several meetings of the standardization body. This already probably existed. Then they designed them all the way to here. And then a few years later or decades later, they came up with these two. And we don't have anything below that, right? Yet, probably it's going to come because I know that some physicists are already starting to use W, X, and so on in some high energy physics papers. Okay, this you don't need to know, don't worry. It's just that since computer scientists love powers of 2 so much, we had at some point to also invent prefixes for that. There's just actually a nice coincidence that 2 to the power of 10, which is 1024, is incredibly close to 10 to the power of 3. And that's actually because this is so close that we have these 2 ways of counting, either as powers of 3 in increments of 3 zeros, or the powers of 2 in increments of 10, right? But this is what you need to know, this one, with the powers of 10. Okay. So when you have an information system, actually, typically, you have a front end. Very often, that's a website, like an online shop or a library or anything, right? So you have a front end. But the important part is what's behind this, because the front end is just not there by magic, right? There's actually a whole, it's only in a Harry Potter movie that maybe you'd have a front end on its own, right? But in reality, we have an information system behind that actually stores the information. And you probably noticed how even with hundreds of millions of products in there, when you look for a product, the page displays instantly. Imagine in 2022, you look in millions of products, it's instant. Imagine how hard that would have been thousands of years ago. We already had libraries, right? Alexandria and so on, we already had libraries. It just took a bit more time. There were already indices and so on that were accelerated. But here now, it's amazingly fast when we search that. And this is thanks to the information system. So how does it look like? Wait, you might think, okay, maybe we can use Python and query the data on the drive and build a website like that. I'm going to disappoint you, this is going to be slow. You are not going to get a performance to actually get this in just a few milliseconds if you try it that way. So I'm going to motivate now why we actually do have database systems and information systems that are not just an imperative language directly querying from the disk. A first motivation is that if you would do it that way, then you would probably have hundreds of people in the same company doing the same, right? So imagine that some in the payroll, in HR, they have some Python program reading from the disk. Then the same in the other department, right? In the products, in the inventory department, they also have their own system. Oh, that would be the list, and that would be the inventory, so the stock that there actually is. This would be the online shop. So you see, everybody has their system. But then you have some problems. First, you might have redundancy, because you might have data that is stored here as well as there. So it's stored twice. And if you have redundancy, that usually comes along with another problem, is that you might have inconsistencies in this information that is stored twice. Because maybe at some point the information is more up to date in some system, and the other system doesn't have yet the latest information. So you see, this is a big problem. You're redundant and you're inconsistent, right, if you try to do things that way. And also, if somebody comes and says, okay, let's try to analyze some data from both the payroll and the products, this is hard to combine because these systems are isolated. They were programmed by different people, in a way that doesn't combine easily. So if you want to actually join, we'll see what join means in this lecture. If you want to join the data here and here, it's actually not easy to do. It's not easy to do at all, right? So this is why we need a database management system. Database management system is the key word. So I have a top 5 of why. The first one is that this system can enforce integrity constraints. It can check for you that, for example, some numbers are always positive, or that a birth date will also always be in the format of a date, or that all the, I don't know, the inventory, the quantities are all integers, you know, that sort of things. If you have a database management system, you can just tell it just once that it's supposed to check that, and then it will do it for you. If anybody tries to change the data or enter data that doesn't fit these constraints, it will be an error, and that will be impossible to do. So that's already a quality management, you know, for consistency. Second, when you are a company, you typically have multiple employees. If you are an international corporation, probably even tens of thousands. If you just go ahead and program and write a program, if you are the only one using it, that's fine. If you have 1,000 other people who try to access the same data with your program from the same disk, that doesn't work. With a database management system, you have native support for multiple users. You can have thousands of people connecting to the same database, and it will just work. And really just work, right? Because this is all, there's decades of work that went into building these systems in order to make it work in that way. Number 3 is that it avoids the data loss, because these systems are able to replicate or duplicate the data to organize regular backups in some way or some other. So you also avoid the data loss, which is very important, especially if you're a company, you need to protect your data against loss. All right. Number 2 is supporting access control, because maybe you don't want anybody to access the data. You don't want people outside the company to access the data. You also may not want everybody in the company to access the data. Maybe you want, I don't know, the financial reports to only be writable by the accounting department, right? Maybe you also do not want the payroll to be visible by everybody in the company, right? So the database management system will allow you to say exactly whose account has read or write access to what data. This is also something you get in a database management system. You do not get that by directly writing a program reading from the disk. And finally, and that's the number 1, the top one, is that it's much cheaper. It's much, much, much cheaper than the hours of time that you are going to spend writing a program, because what you are going to write, in fact, has already been done by other people. You're just redoing the same work. You're saving costs by using a database management system, not only because of this, because you don't have to do it, it's already taken care of, but also because it's going to be faster, because it's implemented in a way that it's fast. It's going to be more productive, because you have a query language that has been designed in order to be productive. And lastly, there are free and open source systems. PostgreSQL, for example, you can download for free, right? So it's just available, it's out there. SQL, the language that we will use, is a standard. So this is the top 5 of why we need a database management system, and why I will teach that to you so that you can use that kind of system as part of a thesis, you know, semester project, master's thesis, PhD thesis. In many, many, many cases, not all of them, of course, in some cases maybe that doesn't work, but in 80% of the use cases, a database management system, and in particular, a relational database management system, is all you need. Okay, so here I had another question. Okay. So just to see if some of you are already have some degree of familiarity with relational databases and SQL. So what is this? I've heard of it. I have programmed personal websites, or I already know everything about it. All right, that looks good. So if you said, what is this? That's okay. I'm going to explain to you in 14 weeks what this all is. If you've heard of it, that's perfect. Now you're going to see it in action and how that works. If you've already programmed the website, that's great. Now you're going to dive deeper into how to use a system like that. There's nobody who actually picked the fourth answer, but even that would have been okay, because you might have power users that are very good at actually programming or using SQL, but who lack the theory, right? And so in this course, you will also have some theory in there. All right, let me now come back. This one right there. There you go. All right, so let's now start with the first idea of having some data stored on disk, and we have something that manages and knows about the data stored on disk. Well, first, here's what happens in reality. In reality, we usually do that in 3 layers. The persistency layer, so that's what write and reads from disk. We have a business logic layer that basically deals with when you order on the website to make sure to do the logic of checking that there's inventory and filling the cart and registering the order and so on. So that's typically programmed in Java or PHP, as we will see. And the user interface, that's typically HTML, CSS, JavaScript, and so on. Right? So this is basically the 3-tier architecture as it is known. And typically what you have when you have payroll, accounting, the store front end, the inventory, and so on, what actually happens is that this level here, the persistency layer, is unified. So here we have a database here. What does database mean? It's not a system. The database is the data itself. When you say database, that's the data. But what you have, so that the database here, that's the logical view that Edgar Code envisioned in the 1970s. That's viewed as just tables with rows and columns that are actually stored on disk right there. But you view that as a unique database that everybody shares. Plus, that layer right here, the persistency layer, is also shared. That's the database management system that takes care of the persistency level. All of that is then shared by everybody. It's maintained for the entire company, ideally, right? And then this is what we call a database system. It's all of that right there, the database system. It's the database, the data itself, plus the computer program that actually deals with the management of that data, right? So I repeat, 3 things in there. The database is the data itself. The database management system is the computer program that deals with the data and hides the complexity from the user. And the database system is everything. It's a system just like, an ecosystem, a biological system, and so on. It's just that it's a database system, okay? So database system is everything there. And of course, that stays outside. So the logic in Java, PHP, or JavaScript stays outside, but everything related to the data is now integrated. So now, this notion of data independence that Edgar Code brilliantly suggested in 1970 is the idea that in a database system, the way you should do things is in 2 layers. You have a logical layer and a physical layer, right? So the logical layer is that when you access the system from above as a user, you see tables, also called relationships, and deal with tables. The physical level, the physical layer is writing to disk, but these people, they don't know about it. This is all taken care of for you by the system. And so this idea of saying we should have these 2 sites independently of each other is Edgar Code's idea in 1970, the seeding paper of modern databases, the modern database era, right? And the idea of data independence is, again, you have the logical data model, the table, and the physical storage, which was in the 60s, just files and directories on the hard drive. However, this also works with clay tablets. They might not have known it back then, but a clay tablet is also a physical implementation of the relational model. It's just maybe a bit slower, especially to write data on that layer, but it works. It's the same. You could also have a cluster of machines. In big data for engineers, this is what we have. You could also have DNA. In fact, people here at ETH, in collaboration with other universities, I think Imperial College, they managed to store relational tables in DNA and to execute SQL queries directly on the DNA. That's amazing research. But just to say, this is the power of data independence. You can switch the implementation right there. This doesn't change. This is the same language, the same model, and so on. This is why it's so powerful. So when you have a logical schema right here, you have always the physical layer right there, that is the directory and files on the drive. This is all the scary things that as a user, you don't even want to know about because the database management system will do it for you. Then you have this conceptual layer, which is the upper part of the data independence, where you think in terms of tables, schemas, and so on. And here you have 1 degree of data independence, right? That the first computer system deals with that. And here what you see is structure. I'll come back to that, the schema, the types of the columns, the constraint that you want to have in there. This changes rarely, right? The schemas. You set them up maybe for a few months or for a few years. And finally, you have an additional layer. So this would be the external layer with HTML, CSS, JavaScript, the forms that you have on the website that communicate with the database. So this is, again, the 3-tier architecture I told you about, right? The persistency layer that deals with the physical layer. Then you have in between the business logic layer that deals with accessing the tables and so on. And then you have the front-end layer with JavaScript, CSS, and so on. You could argue that this can also be seen as a different form of data independence as well, that the website also is kind of independent of the relational database. In fact, many companies change the front end. It's basically the lipstick of the website. They change it without actually changing the database. So you basically get data independence twice in a way, right? You have data independence in the true sense of it right there, and a second data independence instantiation right there. Okay, so what you have typically is masks, views, and so on. In many companies, you might even have desktop apps that are accessing the data with all kinds of formulas and so on, which might be familiar to you. This changes maybe a bit more often. Okay, so here you think in files. Here you think in tables, and here you think in terms of applications or web applications or smartphone applications now. Okay. So now, what do people do in a database system? Because obviously it's been there for 50 years. Every company in the world has one, so it generates jobs, right? So what are the jobs that this generates? Well, you have people who are dealing with the maintenance of the system, monitoring, checking that it works, doing the backup, setting up the access control. So these are the database administrators, right? There's a few in every company or just one, and they deal with making sure that all of that is installed, works, is up to date, and so on. Then you have people who design the schemas of the tables that you put in there, right? So these are database designers. They know about the normal forms and database design theory that I'm going to teach you. And they do these diagrams in order to decide how the data is going to look like. So the model, the data models. You have power users. The power users, these are those who code in Java and JavaScript and full stack developer, if you want to call them, and so on. It's kind of a cool name right now. So full stack developers who actually program over the entire stack, and they are able to build some very fancy and elaborate websites that connect to the database management system. They will probably use SQL as well, but probably also more in the form of programming APIs, which can also be data frames APIs, and so on and so on. And then you have the data analysts, data scientists, who are maybe with a Jupyter notebook connected to the database and writing SQL queries, maybe a bit of Python for visualization. It's actually very, very powerful for visualizing things. So think of working on a Jupyter notebook, accessing the database like that. This might be you, in fact, in your semester project, master's thesis, PhD thesis. So this probably would be the most important one. But what you need to understand is that if instead of just programming, reading from disk with Python, you actually have PostgreSQL or relational system, you basically have this doing all the work for you, and you can just focus on your actual queries and data modeling from right there. And then there's also parametric users. We also call them, I think, data entry clerks or something. So it's people who directly, via some user interfaces, manipulate, enter data, add entries, remove entries. In call centers, you probably have a lot of these jobs, for example. Okay, still have a few minutes. So the database architecture now, as I said, looks like this. This is the whole database system. I'm repeating, right? I love to repeat. This is how you learn. So the database system, the database, which is the data itself, the database management system, which is the actual computer program, The database itself can be on your local hard drive. Yes, you can have that on your laptop. It can be a server shared by people, works with a few people, can be a network shared drive, or you don't see it, it can be a distributed file system like cloud storage, accessible by millions of people. So on the high level, this is really, really high level. So it's almost like I'm just waving my hands there, basically explaining how that works, but we'll dive into the details. You have the data. Inside the management system, you have some data manager and a data manipulation language. That's how you describe your tables. The same for the metadata. This is how you describe the schema, the columns, the types, and so on. And then you have a data definition language, right? So manipulation, you insert data, you delete data, you manipulate data. Definition, you say what your columns are, what your types are, what your constraints are. And all of that together gives you an overall architecture with the language that will be SQL, actually, in practice, this part right there. And we'll see that in 1 week, we'll study also transactions, which is just how you orchestrate when many people access concurrently the same data, avoiding some of the problems that it can cause. Now, in order to finish, I have a few words on just to give you an impression of what this data definition language is, so the schemas. What do you have in a schema? You have the structure, meaning the names of the columns. You have the types of the columns, integer, string, data, and so on. And you have integrity constraints, like this must be positive, the sum of these two must be this, and blah, blah, blah. So this is the schema of a table. Looks like this. If now I give you a concrete example, so that would be a schema with 3 columns. These are the names: customer ID, security ID, quantity. That might be an online broker, for example. Here we have an integer, that's the types, integer, string, positive integer, and an integrity constraint to ensure the positivity that is greater than 0, right? And that would be the actual data, you see? So that's the schema, and that's the actual data where you have the rows and the records that store that data. And then, of course, you add data, you remove data, you delete data. The one thing that doesn't change is this. This stays the same. You just modify the actual data of in the table right there. And since you have a management system, it will prevent you from doing things like that. This will not, you will not even be able to do that. Right? It's taken care of checking that for you. So as the system evolves and people buy stuff and you need to adapt the inventory and so on, tables have a life, and there is a cycle, like their life cycle, that's called the table universe within a schema. Okay. Now, in terms of DML, what you need to understand is that on the high level, there are 2 kinds of languages: imperative languages, declarative languages. Imperative is a recipe. Put so and so much butter and add some sugar and add some, the flour and the eggs and blah, blah, blah. That's a recipe. That's an imperative language that you find in a recipe. Declarative language means, like you are about to do, going to the Mensa and asking for the veggie menu or the menu 1 and so on, right? So this is declarative. That's the difference. Python, C++, Java, these are all imperative languages where you have to give specific instructions on what to do. A declarative language, including SQL, provides you a high-level way. It's like, again, going to the Mensa and asking for the menu instead of cooking yourself. This is the declarative languages. So typically, here it's assembly code. You won't even deal with it. C++, Java is for power users, full-stack developers, and so on. And SQL is the convenience of querying on a high level, as we will learn. Thanks to SQL, again, data independence, you just say what you want, the physical execution, automatic. The system will figure it out for you. It will come up with a plan to execute it. And we'll see in big data for engineers, you can even parallelize that on hundreds of machines very easily with exactly the same SQL code, which is, in fact, the last slide of today. So now you can go to the Mensa, you can get some good food. I'll see you next week. There's no exercise session, again, this week. I'll see you next week at 10 for the continuation and the relational model. Thank you very much.